Good morning, everyone. Let me welcome those of you who are early risers to the second day of the South African Interferometer Winter School. So we are going to start today off with some lectures on the visibility space on the hand of a two-element interferometer, and they're going to be presented to us by Ben Hugo. Now, Ben is a software developer and a support scientist at Serayo. His interest is galactic cluster evolution, high-performance computing, and radio telescope calibration procedures. He has an MSc that he obtained from UCT University, and he has a background in computer graphics and games development. So let's welcome Ben. Ben, to you.
Thank you so much, Ruby, and thank you for those joining us this morning or evening, wherever you are in the world. Okay, so welcome back to our discussion on radio telescopes and radio interferometers in particular. What we're going to be discussing today is continuing on from what we discussed yesterday, and that is what the interferometer measures. As we said yesterday already, the interferometer doesn't directly measure the brightness distribution of sources on the sky. Instead, what it measures is the spatial frequencies or the projected spatial coherencies of that brightness distribution. Now, we refer to that as the visibilities of the interferometer. And the term, why we use the term visibility will become a bit more apparent during the course of this lecture. So let's move on. So at this point, what we have already covered is the mathematical section that includes the Fourier transform. Which is going to be quite important because we're going to be using the properties of the Fourier transform to construct an interferometer. And then what we've also covered already is the basic introduction to radio telescopes and especially the relationship between the aperture of the antenna and its far fields. We're going to be referring back to that in a bit. All right, just to recap, I'm going to formally define now the coordinate systems which we use. Ruby already gave a very nice introduction onto the sky coordinates and the observer aperture coordinates yesterday. So I'm just going to recap and formally define them because we're going to be referring back from them throughout the lecture. So it's good to have a recap of that. So for the engineers joining us and the scientists and high-performance computing people joining us, I'm just going to recap the basic sky coordinate system. Now, sources very far away, so I'm talking about galactic and extragalactic, is going to move with respect to the rotation axis of the planet. Now, they're going to on what we call the sky celestial sphere, which is a unit sphere just to simplify the mathematics. And what they're going to do is, so they're going to track out circles around the poles of the sphere, which lies directly above the rotation axis of the planet. So that is the north celestial pole, and conversely the south celestial pole, as indicated with my cursor over here. So during the course of a sidereal day, which is about 23 hours, 56 minutes, so just short of a solar day, they will complete a complete revolution. So let's say they start off at the north-south meridian of the observatory, right? So the sky directly overhead of the observer, and they're close to the north celestial pole. Then what they're going to do is they're going to track out a circle during the course of this sidereal day, right? Okay, the offset of that circle with respect to the horizon of the celestial horizon is what we call the declination angle, right? So you can see that the offset from this horizon to such a star is going to be indicated by this declination or delta angle over here on the great circle, right? So this is, so they'll be tracking out circles that is parallel at this declination hand over the course of this sidereal day, right? Now, this is one of the angles that we need to be able to track the source. What we also need to know is when the source will pass overhead. Well, we can work that out. The observatory is going to keep a clock to some internationally agreed upon meridian. So let's say, for instance, the vernal equinox, right? And that is indicated here as the first point of Aries here on this point here. Now, the angle between that meridian and the source, right? So along this celestial equator is known as the right ascension, right? And it's indicated by alpha, right? Now, if we have the clock of the observatory, so the local sidereal time to this meridian, so the time that it will take for that meridian to pass directly overhead of the observer, now then we can work out the hour angle it will take for that particular source to pass overhead of the observer, so pass overhead through this north-south meridian. And that's all we need to know to be able to track sources on the sky, right? So we can work out its hour angle, and we have its. Now, if the observer is right at the rotational axis of the planet, so the rotational pole, then that's all we're going to need to be able to track sources. But if you're anywhere else on the planet, then your horizon, so the observer's horizon, indicated here by horizon here, so this horizon, is going to be slightly offset from the celestial horizon, so the rotational horizon of the planet. Now, so we can go from the right ascension and the declination angles to the azimuth and the apparent elevation angles as a function of time if we know the observer's latitude. So this is indicated here in the matrix on the right-hand side. So if we know the observer's latitude, L of A, we can basically work out the elevation and the azimuth of the source. So this is given by this matrix over here. So let's say you have 2 points on a big aperture, or equivalently, as we'll see in this lecture, 2 different antennas. Then we can define a vector between those 2 points. So let's call that a baseline. And that baseline is fully defined by an azimuth angle to the projected component onto the local horizon of the observer, and an elevation angle along the great circle up to the zenith position here, directly overhead. Now, the azimuth angle is always going to be defined north through east, right? Right, and then what we could do then is we can use the known latitude of the observer and tilt this local horizon into the celestial horizon. So everything's going to be tilted to be parallel to the rotation axis of the Earth, right? And then what we're going to have is this X, Y, Z frame over here, which is the nominal celestial frame. So X points south, Y points east, and normally we define the Z direction, so the orthogonal direction to that, to point towards NCP. So in terms of increasing declination. Then how do we track the source? Well, we use the matrix on the left-hand side here, which you already have seen yesterday, which is going to be dependent on the hour angle, so H naught of that source, which we can work out from the sources right ascension and given the local sidereal clock of the observatory and its declination, right? So all that matrix here does, it's basically a concatenation of 3 different rotation matrices. That is simply going to rotate us into this UVW frame, where W points towards the source that we want to track at any instant in time. So this is just the rotation of this equatorial frame that we've already rotated the different spatial measurements into, right? So then we just scale this by the baseline length, so the distance between these 2 points on an aperture, or between two different antennas. And then also note, very importantly, that we always measure this baseline in terms of the observed wavelength. Right? Okay, and that essentially defines the coordinates both on the sky that we're tracking and the coordinates of the that we're using to track the sky. Now, as I've shown already, the UVW frame is going to be dependent on the hour angle, right? So at different hour angles, the baselines are going to be slightly rotated with respect to a fixed sky, right? So remember that I said the W component of this frame directly points towards the sky. So let's start off at declination 90. So let's say the source is at the NCP. So we're tracking, for instance, Polaris. Then what we're going to have is that the W point towards NCP. So this is 90 degrees. So it's going to point directly upwards here. So W lies along this axis. Now, as we move declinations further and further away from the NCP, you'll see that this frame now starts, right? So as we get very close to declination 0, then the points, as we project them onto the plane UV, W equals 0, so this UV plane here at W 0, will form a straight line in either U or V, depending on the hour angle. Now, this is if we have a perfectly aligned east-west interferometer, such as the Westerbork synthesis radio telescope here in the Netherlands. So, for such an interferometer, all the spatial coherences or the spatial frequencies that we measure is going to lie on a single plane inside the space, and therefore, if we're at low declination, they're going to all lie mostly on just one line through this space. Now, this is why we need to put in north-south spacings, which we'll have for Meerkat or the VLA or ASCAP and so forth, and that will measure spatial coherences in the other parts of that UVW north plane. However, those measurements don't lie in a single plane in this three-dimensional space anymore, and it breaks the direct Fourier relationship that we have with the going between the sky and what we measure with the telescope, as we've already alluded yesterday. And I'll get onto how to fix that inside the imaging lecture, but for now we can say that if we have a perfectly aligned east-west array, such as WSRT here, we do have a two-dimensional Fourier relationship. I'll get back onto that a bit later on. Now, we've already said yesterday that we have essentially we're tracking different spacing. So let's say between antenna 1 and antenna 2 here, so these first two antennas, that short spacing will lie close to the origin of this UVW space, right? Spacings further away, so from this antenna all the way to the antenna at the far end there, those spacings will lie towards the edge of the UV space. Now, as we'll see a bit later on, those spacings track the fine scale structure in the sky. Also important to note that for each such spacing, so let's say spacing between this antenna and the antenna at the far end, this red line over here that I indicate with my cursor, for each such spacing, we're going to also track the spacing between that antenna at the far end and this first, right? And that is indicated conversely here in the blue spacing, right? Now, because the sky is real, right? It's just a power distribution, right? Such a baseline measures the complex conjugate, and it doesn't really add any information. So we only store one pair, in this case, either the red pair or the blue pair here. Here I'm just plotting a few of these spacings. There's many more, so I'm just making things clear by plotting only a few here. Now, Those are coordinates on the aperture, so the measuring device. So this is indicated here as these U, V, and W coordinates, where W, of course, points towards the point that we're tracking on the sky. Now, we can also define cosines of this frame, right, in the image on the celestial sphere. So these are known as the L, M, and N cosines. Importantly, they lie on the sphere, so they can only range between -1 and +1. So if we have a source that's sitting right at the tracking center of the telescope, it's lying directly in this N direction here. If it's slightly off that tracking center though, so you have a slight offset to say this source over here, just above the lobe, then it's indicated by an offset vector, sigma, in this case, I've indicated over here, and that sigma vector is projected onto our baseline. Now, as our baseline moves because of our angle, we get essentially for free different projections over time. So this is known as Earth synthesis rotation. So, synthesis, sorry. Now, so basically, if we have an offset source here lying off the n-axis here, then we're going to measure 1 minus this new n direction to the source, right? In the last cosine, and an offset in the L and N cosines. Importantly, as I said, these cosines lie on the unit sphere. They only range from -1 to +1. So they shouldn't be confused with the angles and the offset angles between the tracking center and the source position. That can be found out by this spherical trick relationship that I've included here, which says that both the L and M cosines are functions of the declination angle and the right ascension angle. Now, the right ascension naught, so alpha naught, and declination or delta naught points towards the tracking center of the telescope, and alpha and declination points towards this other position on the sky, which coincides with our source. Right. Okay. So that's all you essentially need to know. For now, I'm not going to cover what is known as the world coordinate system at this point. So everything is lying on the unit sphere, in this case, the celestial sphere. There's various different ways that you can project positions of that sphere onto either a tangent plane or a plane that is slanted through the celestial sphere, and onto pixel positions onto such a two-dimensional image plane. So as I said, those are known as the world coordinate system. The library is already implemented inside AstroPy for those of you that are using Python. So we don't need to worry about that. All those transforms are described in a various set of papers. So for those interested, you can go have a look at those papers. Most radio images uses the Syn projection, so the orthogonal projection of the celestial sphere onto a two-dimensional image plane. Now, what this is going to do is essentially, as you go further and further out from the tangent point of that plane on the sphere, your pixel sizes will start increasing, so they will be non-regular. So all of the various transformations to get accurate coordinates of such a image, which we normally have regular pixels at, will be given by this world coordinate system library implementation. So, but that's all I want to say on that topic. Now that we know the various different coordinate systems, we're going to move on to what a radio telescope actually measures. So we're going to start off with a single dish construction, which is known as a radiometer, and we're going to tie that back into what we measure with an interferometer a bit later on. Now, the simplest possible device that we can construct to measure the power of a radio signal that is in the far field is known as a radiometer. Now, a radiometer consists of three primary components. The most important here, I guess, is the antenna itself, which can be a steerable or directional antenna, such we have with Meerkat or ASCAP or VLA, or it can be a simple dipole that you place on the ground that is non-steerable. Case in point is, for instance, LOFAR, right? So we have a measuring device, so the antenna itself. The signal from that measuring device is going to be passed through a bandpass filter, which will only give us a small bit of bandwidth that the antenna is effective at, right? And normally at this point, we also channelize the induced voltages on the system, right? So we end up with channelized voltages here, right? We're going to square those voltages, and we're going to integrate them for some short amount of time, which the sky stays roughly still overhead, right? And the output from that is a power, right? Because what we are measuring is the square of the voltage, right? And in the absence of strong ohmic losses, the square of the voltage is roughly equivalent to power, right? It's also important to note here that the measuring device itself essentially acts as to some extent as a bandpass filter in itself, just because of its physical properties. Now, the engineers out there may be familiar with this already, but I'm going to remind you of the basic transmission line theory, which you'll have a standing wave on a closed transmission line. If you open that transmission line, then you have essentially a dipole that is either vertically or horizontally aligned. Now, that dipole is only going to be sensitive to wavelengths that is four times its physical size. So we refer to this usually as a quarter wave dipole. So it's the physical size of the measuring device, so the dipole in this case, is going to limit the range of frequencies that you're sensitive to. So we usually apply a further filtering on top of this, but I just wanted to point that out. Now, as I said, this radiometer measurement device is going to give us an output power. That output power is going to be proportional to the antenna pattern. So in this case, we have an antenna that is perfectly omnidirectionally sensitive, right? So it's going to be sensitive to any part of the sky, right? So we have this A term over here, right? So this is just the antenna response, right? You can think of that as that. And the source flux density. Now, the source flux density comes from some small portion of along the celestial sphere. So there's some brightness here. Sorry, and it's inducing a voltage here on, so some current on this aperture, right? We indicate the antenna response here by this lobe-like structure, right? Which is, if you have a antenna that is direction independent, it depends on some angle, arbitrary spherical angles here, so theta and phi, right? And usually we define this antenna response to be have a response of unity at its maximum, right, at its peak. Right, so over there we have a unity response. So all we're going to be measuring at this output power is then this antenna pattern times the source flux from some very small portion on the sky. So we can write this as in terms of brightness, right? And if we have a distribution of sources that are all emitting incoherently, then we can say that we can take an integral over the entire sky sphere, right? So 4 pi of the antenna response, right, as a function of angle, the brightness as a function of angle again, right? for each bit of this sky sphere that we're integrating over, right? And this gives us a power measurement in terms of watts per channel, essentially, per unit hertz, right? I also need to note here that the source flux here is as this M suffix over here, which indicates that it's matched to the polarization of the measuring device. So the vertical polarization, for instance, of this brightness over here is measured by a vertically polarized dipole on the ground, right? If you have a source that is emitting unpolarized radiation, then all that means is the source is essentially emitting radiation that has equal chance of going through either the vertical or the horizontal. In that case, if you only have one dipole, so let's say a vertical dipole, then you're going to be measuring only about half of the available power, right? So it's important to realize that the dipole needs to be matched to the radiation that you're trying to measure. All right, a bit more about polarization later on when we start discussing calibration. Now, in terms of the sensitivity that we can achieve on such a system, Ruby already gave a good introduction to that yesterday. Now, the sensitivity depends on the antenna temperature, which is indicated here as TFB, right? And the effective collecting area of the antenna, which is always going to be measured in terms of wavelength, right? If you have a perfect system that has no ohmic losses, it will scale perfectly to match the total collecting area at its peak point of at the peak of the antenna response, right? Anywhere else, we're going to have a drop-off. As I said already, we have for a directional antenna, we'll have a primary lobe in which area it is mostly sensitive. Anywhere else, we'll have minor side lobes, but we'll lose significant sensitivity for a directional antenna system such as a meerkat. Right. Okay, so we can relate this temperatures scaled by the effective collecting area back to specific intensity, so back to Jansky's, for instance, using the classic Rayleigh-Jeans approximation for low frequencies. Now, the frequency range in which we operate at centimeter, millimeter wavelengths is going to work under this Rayleigh-Jeans law. So we'll use this Rayleigh-Jeans approximation to relate between antenna temperature and brightness. Now, B here is known as the system equivalent flux density, the SEFD, and you'll see this throughout the literature. Now, all this indicates is essentially the level of the incident noise on the system. And above this level, we'll be able to detect sources of coherent external emission, right? So a source on the sphere, for instance. Now, that noise is primarily driven by the various amplification stages within the receiver system. So the low noise amplification system has some resistive properties, and it has some temperature, therefore, and it dominates the system temperature, right? So this is why we place this in a cryogenically cooled enclosure to keep things stable and to keep things at a low temperature to lower that noise inside, for instance, the meerkat receivers. It also depends, especially when you move towards the ground, on spillover. So spillover is essentially pickup of emission that stems outside the antenna collecting area. So for instance, the ground is radiating at 300 Kelvin. So it's quite a bright source if you're at really low elevations. If you have a highly directional antenna, such as we have with meerkat, and you point it anywhere else, the antenna lobes will drive down that spillover, essentially. Now, at higher frequencies, we also have the atmospheric temperature coming into play, but this is only mostly a concern at really high frequencies. Now, so a single aperture antenna serves to coherently focus the collected radiation onto a single point, at which we place the receiver. So I think Justin already showed a very nice schematic of how rays are reflected through the primary mirror of Meerkat, first onto the secondary, and then onto the waveguide of the receiver in this talk. So, but essentially, if we think of just a parabolic dish that we place on the ground, it's going to coherently focus radiation between any point on that parabolic dish onto a single point, focus point of the dish, right? So at that point, all the radiation is going to experience constructive interference, right? And it's going to be maximum. So if we know this, then is it we ask the question here, is it possible that we can add more collecting area to lower the noise? Well, the short answer here is yes, but as long as the measured signal can be combined coherently. That is the golden rule here, right? And we'll see this come into play when we take the single dish and split it into many dishes to form an interferometer. Now, of course, we can construct a very, very large dish. Unfortunately, such a dish has a lot of material going into it in order for it to support its own weight, right? So here I show the old 300-foot telescope at Green Bank, and this is before and after its collapse. So the telescope was in operation for just under 3 decades. It was commissioned here in the 1960s, and it collapsed in November 1988. Now, this is a remarkable story of an antenna engineer that's narrowly escaped this collapse of his life. So Greg Monk was sitting in the operations building nighttime doing observation, and the story goes that he heard a very loud rumble, and the next thing he knew, the antenna structure came collapsing through the roof of the engineering building, and he very narrowly escaped with his life. So for those interested, can go and read the story. It's quite a remarkable story. So the reason why why this dish was so large in the first place was to get good sensitivity in order to do things, early work, for instance, in pulsar science. So the instrument did fantastic work in those early days. It mapped out all-sky survey, I believe, so I think it's 6 centimeters. In any case, it's still referred to today, and it also was used to map stellar nurseries, for instance. It's fantastic work, but unfortunately, the one of the plates that was holding it, that was connecting various parts of the structure, cracked, and that wasn't detected in time, so it ultimately collapsed. Now, coming back to the response that we've described yesterday, so remember that we said that there is a roughly Fourier relationship between the aperture of the antenna and its response in the far field. I'm just going to recap that relationship here. So this is indicated here by this first equation. So over here we have a function g u of v. So this is the aperture function, and it's essentially the distribution of current in this UV frame that we've defined, and has a roughly Fourier relationship. So you'll have this u dotted dotted of L, V dotted of N, W dotted of N between this grating space, so this G space and its far field response, which is F of L and M as we defined it previously. So in both cases, W and N point towards the source. So just keep that in mind. The N cosine over here is there just because we've converted between a solid angle integral and a integral over two-dimensional space. So this is just the determinant of the Jacobian. And we can convert this far field response into power by squaring it, and we typically normalize it such that that response is going to be unity at its peak. The antenna has losses, which is indicated here by this N over here. All right. As I said, the antenna has is measuring at some frequency, so this is indicated here by wavelength lambda. Now, so I've shown some examples here on the left-hand side of the grading function. Let's constrain ourselves just to 1D here. So let's call this X, where X can be either U or L, or anywhere in between, if you like. Now, the grading function, so the current distribution here on the aperture is indicated here on the left. On the right, we have the far field response that corresponds to the aperture that looks like that. So we can see that there's various responses that have slightly lower side lobes, right? Could be a property that's very useful. So, but in all cases, there is a Fourier relationship between what we measure. So a box-like thing will be looking like a sinc function. So if you look at from the top down onto a meerkat dish, then it will roughly look like, well, almost like a pull box. So it will have something looking like a sinc response, right? In the voltage response, if we square that, we get its power response, right? And that's what we indicate here by the A of L and M, right? So some of these examples are non-uniformly graded, right? So there's holes in them, and this can correspond to something that's built in real life. So a very good example of where we have non-uniform grading along the surface of the aperture is the Northern Cross in Italy. So it's near Bologna. Now, the interferometer here consists of two arms, right? And for each of these arms, we have very thin strands of wire horizontally spanning between the arms of each of these dishes, right? So you can't see this in the picture here, but there is very thin horizontal strands of wire on the aperture here, and those horizontal strands of wire are matched to the series of dipoles placed here in this focus bar here at the top, right? So remember that we need to match everything to the polarization of the measuring dipoles here. So this will only be sensitive to horizontally polarized light in this case, right? The telescope has a combined collecting area of about 30,000 square meters, so it's quite large, and it's operating at 408 megahertz. Now, so that's one example where you have non-uniform grading on the aperture, right? So just to tie this back to real world, well, we can now refer also back to the properties of the Fourier transform that we've described yesterday, and we can sort of see, if we look at this grading pattern here at the top in the first example, which is basically just two boxes physically separated where there's no there's essentially no reflecting area, so there's no current, right? This sort of starts to resemble how we can construct an interferometer using bits of grading function that is physically separated. Now, what we're going to be using especially is the addition theorem, which says because the Fourier transform is a linear transform, the sum of two Fourier transforms of two signals is the Fourier transform of the sum of those signals. Right? So we can say that we can construct the Fourier response of such a grading function by adding the individual Fourier transforms here. We also then rely on the shift theorem, of course. So that says that the signal can be steered. So if you have a signal on the sky, for instance, you can steer the sky overhead to be maximally sensitive at any point by adding a cosine in, for instance, the grading space here. Right? So we're going to be relying on those two theorems, especially when we construct our interferometer. There's also a third theorem that I just want to remind you of, that's the convolution theorem. Now, that says that a convolution in one domain is just a multiplication in its Fourier domain. So the logical next step that we can take is to delay the measured signal of one grading with respect to the other, and we can construct a basic interferometer. This brings us to the Coherence Sum Interferometer. Now, such as an interferometer is constructed using multiple antennas. We can say each of these are bits of grading, right? So there's antenna P as its grading, antenna Q can have a different grading, but let's say, for instance, they all have roughly the same grading. We can in number of such antennas, but I'm only going to show two antennas here. Now, this setup here that I show is known as the Coherence Sum Interferometer. It's also known as the Coherent Beamformer or the Coherent Phased Array, which Marisa will probably refer to a bit later on in her lecture. Now, such an interferometer has an additional component here. So this exponent that depends on tau. Tau is given by a delay tracking computer, which just gives us Wn-1. So 1 points towards normally where each of these antennas and the interferometer is going to be nominally sensitive. If you want to have it sensitive towards any other point on the sky, so any other direction in, then the delay difference, bit of cable essentially you can think of between these antennas connecting them to a integrator, so a sum here, is going to be given by this delay term. This is purely geometric. There's at this point no forms of calibration error, right? So this is just a pure geometric relationship, and it essentially moves the antennas up and down with respect to some reference point. Let's say the reference point is picked to be the first antenna in such an array. Then if we've introduced this delay, then all the antennas in such an array is going to coherently measure the induced voltage from the incoming wavefront from a source in the far field between any two antennas, right? So the induced voltage is going to be measured at exactly the same time on this antenna P as it would be on this antenna Q. Let's call them P and Q in this case. The antennas are separated by some distance, so there's a baseline distance here in this UV space, as we've defined them earlier on. And now, as I said, the delay tracking computer has compensated for the geometry of the problem, such that we get a signal that has equal path length between the antenna P and the antenna Q to the sum here. So we're adding coherently the signals, the induced voltages between these two antennas, and we can scale it, of course, to any number of antennas. We then square that integrated voltage, and out comes some power, exactly as we had with a radiometer earlier on. So if we express this in terms of mathematics, so we say that we get a power out from n coherently summed antenna. Why is it coherent? Why? we have this exponential term that has the delay term, and the delay tracking computer for each antenna in such an array is keeping track as a function of time. Remember that W is our angle dependent, of course, so it's keeping track as a function of time the direction, so the projected direction towards the source, given by this n vector over here. Now, if we have a delta scale source, so a point source on the sky of some brightness, right? So this has some power already. So we've removed the square here. We're indicating this as brightness. So this is in terms of watts. That source is placed directly in the direction of n, so where the interferometer is steered to be maximally sensitive. Then what we're going to be measuring for a point source, so unresolved source, is going to be just the grating function. So essentially the square of the Fourier transform. So I'm missing a square term over here. So square of the Fourier transform of the far field response that gives us essentially the power response in the UV space. And if that is roughly constant over the source, as we assume, so for a point-like source, then it's just a multiplication. And so we just have a scaling of this brightness placed along this direction in here, right? In this case, the far field response is, say, unsteerable antenna. Let's say a dipole on the ground that can't be physically steered. It has a maximal response somewhere else on the sky, so direction, directly upwards, for instance. So in this case, L prime and N prime are not pointing towards the source, right? So this is just one example of how you can construct this. If you have a steerable antenna, let's say we point this L prime and N prime towards a source of the pointing center of the interferometer, so the tracking center of the interferometer, then what we're going to have is the far field response towards L prime and N prime, and the brightness L prime N prime multiplied by a cosine. Remember that if we have a direct delta in the sky space, its Fourier space is going to be a fringe, right? So it's going to have a cosine and sine component attached to it, right? In the most generic case, such if the antenna is response not quite constant over the entire extent of the source, then we're going to have a convolution between the square of this grating function with the brightness, right? And of course, the exponent tau term here is exactly the same throughout, right? It's just the delay tracking towards the direction in, right? Under uniform illumination of the two orthogonal polarizations, normally we have two orthogonal polarizations fully describing the measured polarized signal, such a sensitivity from such a construction is going to scale as the collecting area times the number of antennas if we have a homogeneous array of antennas. So if we have, for instance, the meerkat array where all the antennas are roughly the same, then the sensitivity is roughly going to scale as n times the total collecting area in wavelength, right? So as we add more and more antennas, our sensitivity improves substantially, right? This is only the case because we are adding the signals coherently. So we have this delay tracking computer in here. If that is not the case, then this n term over here moves inside the integral, where the rest of the integral is given by the integrating bandwidth, so delta nu, and delta t corresponds to the integrating time, right? So in such a case, we don't really get an improvement in terms of sensitivity because the signal is not added coherently. That is known as incoherent beamformer. I'm not going to go into much further discussion on this. More details will be provided by Marisa. Now, so this essentially ties the sum interferometer back to what we had with a single dish, approximately equivalent to having a single large unfold aperture where our grading function just has holes and things in the middle of the constructed aperture. This brings us to the product correlator. Now, we can do slightly better than the sum correlator. So this coherent beamformer, as we just discussed, by also including all the phase information between various different spacings. So if we have, say, the Cat7 array here, which is 7 antennas, then if we include all the phases of all these spacings, then what we get is known as the two-point product correlator. Now, in such a correlator system, we are measuring both the brightness of the source, right? So the source, again, is in the far field, right? So we have a planar wave, right? At the point where we are actually taking the antennas are separated by some distance, as we have over here. So, for instance, this maximum distance C here between these two antennas, right? So they're physically separated, right? In this case, we have a homogeneous array, so the grading functions of each of these antennas are roughly the same, right? And what we're measuring then is the brightness of the source and the delay difference between the wavefront as it's traveling through free space, hitting the first antenna, let's say this antenna over here, and the delay for that, the time taken for that signal to essentially induce the voltage on this antenna here, right? So that is this delay term. The delay term is just a dot product of the source offset vector. So remember, we're pointing the interferometer itself, right? Not necessarily the dishes, but the interferometer is being pointed towards this S0 direction here. So you can think of this as direction in, right? It lies in the direction of W, as we said before. And we're measuring for tau the projection of this source difference vector between the source vector and S0 onto the baseline vector B here, right? So this is just a normal dot product, as you would have seen this from your university calculus. And as I said before, the baseline length is always going to be measured in terms of wavelength, right? Now, what this interferometer is going to see, right, is, as I said, the brightness, and for an offset source such as we have over here, the cosine of the delay, right? We also have the gain, so we have a direction independent electronic gain term, which is dependent on time and frequency. We have a direction dependent gain term, which can be again the square of the grading. So the antenna response is one of the primary gains, essentially direction dependent gains that we have for a highly directional system such as meerkat or ASCAP. Let's for now ignore these terms. We'll come back to them in our calibration lecture. Within this interferometer, we again have the phase tracking computer, which steers the interferometer, right, on the sky by injecting a complex exponent, right? And what we also typically have for such a correlation system is injection of 90 degrees here between as the output on the system. So we have both a cosine measurement and a sine measurement, right? Why we need this is essentially the cosine is going to be maximally sensitive in only a small fraction of the sky, where that interferometer response goes to zero, so where the cosine goes to a null. We also want to capture some signal, so we also measure the sine component, right, which will capture signal within that null. This also serves to measure a deconstruction of all the even and the odd components of the sky frequency distribution, right? As we said before, this essentially synthesizes an aperture, an unfold aperture, where the aperture size depends on the longest spacing, right? So B longest here is given by this here, and it's about 185 meters in the case of Cat7. So the resolution is going to be roughly, scale roughly as the observing wavelength over this longest spacing. Here I'm just showing 3 of the possible 28 such spacings. How do I get to 28? Well, there are n times n minus 1 over 2 plus n unique spacings or baselines in such an array. This n over here is the number of antennas. This first bit here, n minus 1 over 2, is the number of cross correlation products. So where we take the correlation between this antenna and that antenna, so for unique antennas. And the n term over here describes the cross correlation between each antenna with itself, right? So there are n such autocorrelation products, right? That typically correlates, for instance, the low noise amplification circuitry within this antenna, for instance, with itself. So we get coherent noise from our measuring equipment. So typically we discard those measurements because those coherent noise measurements don't scale down with time, right? However, those spacings, if we autocorrelate, so each antenna with itself gives us a measurement along the at the origin of the UV plane, plus or minus half the dish diameter. So this is referred to as the zero spacing. If you want to have a measurement of the average temperature of the sky distribution, then you need those. They're typically used in H1 intensity mapping, for instance, where you have really broad scales that you're trying to capture. So if we discard them, then our interferometer becomes sensitive to essentially spatial frequencies off this mean measurement, which we don't include. Okay, just continuing onwards. So as I said, the cosine will have a maximal response, right where the antenna, where this interferometer system is phase steered towards. So this is not vector. Anywhere off that, it will start dropping down, and then it will. The next maximum is going to be an integral multiple of pi here. At those points, we also capture a Syn measurement, so a measurement that's delayed in phase by 90 degrees. Right? You're going to disregard the gain terms over here for now, and so this essentially induces these terms essentially induces a fringe over the brightness distribution, and we're for each pair of antennas we're only seeing a fringe, right? And I'll show you some examples a bit later on. Now, also note here that typically what we do is, as I said before, we channelize the induced voltages on each of these antennas before we correlate it, right? So such a system, as Justin has shown before for the Meerkat system, is known as an FX correlator, right? So we have a Fourier transform of the time signal, the time voltages, before we multiply them in that Fourier space. Now, channelized space shouldn't be confused with the geometric Fourier relationship we get purely from this delay term that we're measuring here. We can measure this geometric Fourier relationship, so that the spatial frequencies of the sky brightness distribution, either in the lag space or by channelizing the voltages, right? So that's just something to keep in mind. Please don't confuse those two. Okay, so essentially, as I said before, the interferometer is essentially a reverse of a double slit experiment, right? So if we have a source that's offset, we see a fringe instead of a source over here. So if we're observing through such an interferometer, then for each pair, for any point in time, we only have one fringe, right? If we have, because we have W depending on the hour angle, right? So our baseline is hour angle dependent, then we're going to be seeing tilted fringes over time. So this essentially gives us more and more spatial frequencies as we add more and more antennas to such a system. So and that scales the number of spatial frequency measurements by roughly the square of the number of antennas. Then we start having more and more fringes of various scales, and we can start to, localizing the source. Also important to note that there is a two-dimensional Fourier or image relationship between the sky and what we measure, right? But this only holds for east-west interferometers that is built on level ground, right? It does not hold if you add any spacings off perfect east-west, so any north-south spacings such that we have with the VLA or Meerkat or SCAP, for instance, right? The reason why this is that the W term, which we had previously, if we just flip back quickly, indicated over here, but the W term that we have, never mind. The W term that we have inside the complex exponential is can be rewritten in terms of linear combination of the original L and M, right? And in this case, we again have a simple two-dimensional Fourier relationship between the visibility or the grating, the interferometer grating in U and V, and the sky brightness distribution, L and M, right? This linear relationship can be applied to all spatial frequency measurements, and in such a Fourier, the linearity of the Fourier transform relationship doesn't break down, right? This is, as I said, is not the case for east-west, for non-east-west arrays. So I'll get back onto that during the imaging discussion and show you how to mitigate for it. Now, getting onto the fringe stopping, we can, as I said before, we can steer the interferometer to be maximally sensitive so that cosine component can be unity anywhere along the sky, right? By just introducing a complex exponential in the interferometer grating, right? That complex exponential, depending on tau, where tau is the dot product of the sky, the source offset vector towards our tracking center of the telescope, and onto the baseline vector, needs to be updated by this relationship here. So B, just the baseline length in this case. So if we have a larger baseline length, we need to update more quickly, multiplied by the sidereal rate, so of the Earth, so that's about 15 degrees an hour, roughly, divided by lambda. So as I said, baseline is always measured in terms of the observed wavelength, and so this, and then we have this relationship also depends on how far the source is offset from the tracking center of the telescope. So if we want to observe sources that are offset by, let's say, a degree from our tracking center, then we need to update at a rate appropriate for that, given by this Nyquist relationship here. Now, as I said, we inject a complex exponential to do this. So we measure the brightness of the source by a fringe, right? So where tau naught points towards the source, TG is the stopping center of the telescope, right? So this is where the telescope will be maximally sensitive, right? So this is coming back to the shift theorem, as we've discussed this before. This is normally done pre-correlation, right? We inject these delays prior to correlating and squaring the voltages to get an amplitude out. All right. Then, because we also have a box response, both in time and in frequency, so if we integrate for, say, 8 seconds and the sky stays roughly roughly the same within that interval, and our system gains and things are all roughly the same within that interval, we get a integration over a box, right? This is a you can think of as a unweighted mean, right? It's just the sum over a box, right? If you think of this in discrete space. Now, such a integral is again a convolution, right? So if we have a box convolution in one space, we're going to have sinc function in the other, right? If you recall the Fourier relationship between a box and the sinc, then what we're going to have is not only does our antenna itself modulate the brightness response of the system, we also have a modulation because of this integration interval that we have in time, also in frequency over here, for instance, right? Delta nu is just half the effective bandwidth of the system, right? So about 400 megahertz in case of meerkat L band, right? So in case of the coarse channelization, so at 0.28 megahertz, the interferometer, not the antennas, the interferometer itself is maximally sensitive only up to this point where it has a null, and that corresponds to roughly about 11 degrees. So we can also expand this to time. Time, of course, depends on hour angle because our so W depends on the hour angle as we've defined it right at the top with our matrix, right? So if we differentiate our matrix, we get these relationships, and then again, because we're integrating over a let's say 8-second interval, our UV coordinates are going to change over that interval, and again we have a sinc function as the response, right? So this makes our interferometer itself only sensitive towards a small portion of the sky. Then we have baseline dependent resolution here, and this is primarily driven by how far your spacings are placed apart. So if you have antennas P and antennas Q, then and they're placed apart by some spacing, so some distance B here, right? Then what we're going to see is a fringe pattern, right? That has a certain spacing, depending on this on this baseline size, right? As we increase the baselines, the fringes becomes more and more compact, right? So here we show a response of a single baseline to an off-axis source, right? So it's a fringe. The fringe period here is going to be defined as the baseline multiplied by the Syn to the offset source over lambda. The fringe spacing, so the spacing between points here, say the troughs of this fringe is given in radians by roughly this relationship lambda over the length of the baseline, and this gives us essentially also the resolution of the telescope. Whenever I refer to UV distance, I refer just to the Euclidean distance of u squared plus v squared, all square rooted. All right. Now, this brings us to some examples, and I think Ruby, if you can read off any questions that we have so far, I just want to get back onto the questions. Yeah.
So here's a question: can you please explain spillover again in the system equivalent flux density calculation, Ben?
Okay, so if we go back to that just for a moment, right? So here's again. So there's various terms that add to the noise on the system, right? The spillover is one of them. Spillover essentially just is any contribution, or it can be defined as any contribution of temperature, right? That doesn't lie or doesn't stem from the aperture of the antenna. So for instance, if we have the antennas pointing in very low elevation, right? what you're going to see is also reflection coming in from the ground, right? And you're going to have the ground temperature itself being picked up by the telescope. That is spillover, right? So that is that's what we define as spillover. Right? But this is only really at low elevations that it becomes a big problem. It's also a bigger problem if you have really small dishes, of course.
Thanks, Ben. And the next question is, can you please just discuss antenna temperature? So just the meaning of antenna temperature. Sorry, Ben, just before you answer that, can I please just ask all the participants, if you have any questions, put them in the Q&A section. The chat is for you to discuss between each other. If you have any questions for our presenters, please put them in the Q&A section. Sorry, Ben, please answer our question about the antenna temperature.
Okay, the antenna temperature is not a physical temperature, right? I should have made that clear, but it's not a physical temperature. It's primarily driven, as I said, by the low noise amplification circuitry that captures the signal, right? So remember that we have a little dipole sitting out there, right? And just below the dipole, we have a low noise amplifier. So we amplify the voltages, right, into a range that we can digitize those voltages, right? Because remember what we said, we want to capture a signal that is really, really, really faint. So we need to amplify that signal, right? We do that with this low noise amplification circuitry, and that circuitry is essentially just can be thought of as a capacitor, right? It's a glorified capacitor. That capacitor is going to have some, well, that circuitry is going to have some resistance. It's going to have some temperature, right? And that is that is captured in this T of B here. And that is, in total, that is the effective temperature of the measuring device, right? And that's what we mostly see for any instantaneous measurement. So let's say for a single 8-second measurement on Meerkat, you're mostly going to see just noise, and that noise is going to be driven by that primarily by your low noise amplification circuitry in the system. I hope that answers the question.
Thank you very much, Ben. And then we have one last question: is how does the time integration and frequency bandwidth affect the amplitude of our off-axis sources?
That's a good question. So let's just go back to that extra slide here. Okay, so the time integration. So let's say you're integrating on Meerkat at 8 seconds, right? Now, that integration interval, right? So where L and M are the cosines to the source. So if we have a source placed exactly at the tracking center of the telescope, so exactly towards in the direction of this vector n that we had previously, right? So then L and M are going to be 0, right? Because they're essentially just the syn of the separation angle. So they're going to be 0. In that case, we don't have any amplitude loss, right? So the original, so the output amplitude, right? So I is going to be exactly the same as original amplitude, 0, right? If we go slightly off that axis and we integrate over time, so where time here really depends on the sidereal rate, right? So if we have spinning at roughly 15 degrees an hour, and we integrate for a few seconds, then what we're going to have is some change, du dt, right? So that the baseline coordinates has now changed underneath the sky. So the projection has changed. So what we're going to get is essentially this sync response, and that tells us by how much the amplitude that we're measuring has dropped with respect to the original amplitude. So for Meerkat, if you average at 8-second interval at L band with the original channelization, let's say of the coarse channelization of 208 kilohertz, then sources 1 to 1.5 degrees away are only going to have an amplitude that's about 90% of the original amplitude, right? So that describes the drop in amplitude. Now, the way you can think of this is why we get this just intuitively. We have a complex number, right? If you take an average of between two vectors on the complex space that are separated by some argument, then the amplitude, so the norm of that geometric averaged complex number will have an amplitude that is diminished. The edge case on that is, for instance, if it's separated by a full 180 degrees, then the geometric mean on the complex space is going to lie exactly at 0, right? So you're going to lose all of your amplitude. So that's just a way to pick why we're getting a loss in amplitude. Okay.
Okay, and then there's a question here. Ben, can you please just explain the fringe washing again?
So the fringe washing. Sorry, Ruby, you dropped there. Can you confirm I should explain the fringe washing?
Yes, can you just explain the fringe washing effect again?
Okay. Fringe washing is what I've just referred to. So this is the drop in amplitude that you get from averaging over time, right? For some integration period, right? The other part of the fringe washing comes from averaging in frequency. So if we channelize in boxes of, let's say, 208 kilohertz, right? Then what we're doing essentially is taking a sum from a frequency minus 208 kilohertz over 2 to a frequency plus 208 kilohertz over 2 here, right? So and we take this sum. Let's discard the gain terms here. Let's say they're unity at this point in time, right? So we're taking the sum of the intensity multiplied by the source fringe for an offset source, right? Where the offset is given by the dot product, as I explained before, right? If we take an average like this, remember this is an average. This is an average over a box, right? You can think of this as an unweighted average, right? If we take an average, right, it's a convolution, right, of the signal, right, over a solid angle, right? So we're going to get out the sinc function here, right? So this sinc function going to serve to modulate this fringe that we see from the source, right? And for meerkat, as I said, it depends on the channelization that you pick. So if you pick 208 kilohertz, so the wideband L-band channelization, for instance, then the first null of this sinc function that you get from this average in frequency is going to have a null at about 11 degrees, right? So this makes the interferometer itself going to be sensitive to a very small portion on scale. Into some examples now that we know what the interferometer measures. Now, let's look at Cygnus A here. Now, Cygnus A is famously bright source. It's a FR2 active galactic nuclei, right? So you have a supermassive black hole sitting here in the middle, and it's spurting out these jets of synchrotron emission, right? And we're going to be observing the source with a 2-element interferometer. We only have 2 spacings here, and we can move these spacings apart. So you can think of having these 2 antennas placed on a track, right? So let's first have a spacing that lies along the U axis, right, just in one dimension, and it's placed at some separation, so some short separation. Now, what we're going to see on the sky is essentially a fringe, right, the source, right? Now, if we integrate over this fringe, what we're going to get is something that is sensitive to mostly the very broad, fluffy stuff here in these jets, right? If we now separate those spacings further apart, so let's say move the 2 antennas here further along the rail, right? So let's say we go from VLA D configuration all the way to A configuration. We move these apart, in just the direction u. So again, now the red dot here just shows the separation along the u-axis. What we're going to have is a much finer fringe, right? Remember that the fringe is given by cosine of tau. As we scale the baseline, tau is going to become bigger, and the cosine is going to become more and more and more compact, right? So this is exactly what we see. So now if we integrate over the fringes that is projected onto the sky, then what we're going to be mostly sensitive to is all the very fine scale structure in the sky. So the nucleus here by itself, the fine scale structures of the jet, so where it drops off rapidly or changes rapidly. So any fine scale structure will be picked up by the longer spacings in the array. So just to go back, so that we can think of the short spacings as being sensitive to the broad scale structure on the sky, whereas the long spacings are sensitive only to the finer scale structures in the sky, and they lay further out in the UV plane. Right? Now we can also take an observation when we let the sky drift overhead for a bit, so at a different hour angle. Now the projected spatial we're going to measure is going to lie somewhere in between u and v, right? So the baseline will have rotated with respect to the sky vector, right? So now, again, we have a short spacing, right, just rotated, and we get a rotated fringe on the sky, right? So just more of the same. If we scale that baseline up, so we move the antennas further apart at that hour angle, we'll again have a finer fringe just rotated, right? So as the sky drifts overhead, we capture many different projections, and each giving us a single fringe, right? If we have a combination of short and long spacings over such an extended observation, then we can start localizing structure on the sky. Now, this brings us to another example. In this example, we'll go back to the apparent scale. So the stellar disk of Betelgeuse was measured back in the 1920s. So here is just a simple thought experiment you can think of a kid of 14 years old standing on the sphere of the star, and he shoots a pellet gun in some direction. Now, if the pellet were to travel all the way around this star, so the entire diameter of the star, by the time it reaches back to this kid, he would have grown to a ripe old age of 70 years old. Just to give you an idea of how big this thing is. Betelgeuse is in the constellation of Orion, so it's Orion Alpha, and it's one of the brightest stars in the night sky. Now, so this cartoon appeared back in 1923, Hutchinson's Splendor of the Heavens. Now, the way we determined the diameter of the star was using an interferometer. The interferometer is the 20-foot interferometer that was constructed at the Mount Wilson Observatory back in the early 1910s to 1920s. Now, in December of 1920, when Michelson and Pierce made an observation with these mirrors, I've indicated the mirrors here are by M1, M2, M3, and M4. These mirrors are adjustable, so when they adjusted these mirrors to a distance of about 121 foot, they saw that the fringes that they got from pointing this interferometer at Betelgeuse disappear. And this is exactly how they measured the diameter of the apparent diameter, or the apparent scale of the star, and then they could relate that to the diameter. Now, the apparent size of the stellar disk of the star is about 47 milliarc seconds, right? So it's really compact. It's plus minus 10% roughly. So if we consider that the star has a parallax of about 18 milliarc seconds, then we can compute the diameter of the star. So we have the distance now. We can compute the diameter, and that's about 386 10 to the 6 kilometers, right? So it's really big. It's about just under the distance to Mars from the center of our sun, for instance. So it's a really big red giant. So here I've shown the schematic illustration of this interferometer. As I said, M1, M2, M3, and M4 are adjustable mirrors. M2 and M3 here in the center is usually placed at some separation, right? And that's roughly fixed. And then what happens is a ray of light, so a pencil of light, comes in and is reflected by mirror 1 to mirror 2. Same happens for mirror 4 to mirror 3. The distance M1 and M2 and the distance M3 and M4 are exactly the same. It has to be the same for this experiment to work. Now, these pencils, or you can call them rays of light, are reflected down onto a primary mirror. Right? Here's a parabolic mirror. It's reflected up to another secondary mirror, right? So it's a Cassegrain design, right? And then that is reflected such that one ray is passed through a adjustable wedge system, which you can use to also rotate the interferometer. And the interference pattern formed between these two rays is focused at the focal point D, right? Okay, so how did they do this? So what we're going to do is repeat this sort of experiment using a radio interferometer. They have taken the wavelength of the light emitted by this source to be about, well, orangey yellowish. So it's about 575 nanometers. What we're going to be doing is working in the radio regime where our wavelength is, say, 21 or so centimeters. Now, for this experiment, we need to define a few measuring quantities. So what we're going to do is measure both the position and the size of the radio source, so the apparent size on the celestial sphere. Now, we have only a two-element interferometer antennas here. We can move them apart, but we only have two antennas. Now, we have a fringe phase defined between these two antennas, and as I said before, this is just a dot product of the separation of the source with respect to the tracking center of the interferometer, right? So this is just the dot product of that source vector onto the baseline, just as we had before, right? In the star term. Now, if we differentiate this phase that we get, then what we're going to see, or the angle with respect to the phase, sorry, then what we're going to get is the fringe rate, right? And that is roughly going to be equal to 2 pi over TFF, where TFF is the fringe period. Now, as I said before, the fringe period is just given by that separation of peaks on this cosine fringe, right? So the fringe period is given roughly for a small angle by just the baseline vector over the observing wavelength, right? So those are the measuring quantities that we're going to take to get positions. Now, we also want to determine the extent, so the apparent scale of the source on the celestial sphere. Now, formally, we're going to define the source to be unresolved if the integral over the fringes contained on the source, so over the source, comes to about 0. This limit is reached when the fringes become more and more compact, right? So I'll show you an example just a bit later on. If we approximate the response of our interferometer by an airy disk, so a Bessel-like function, then the minimal resolvable size is roughly going to be given by 1.22 lambda over the longest spacing, so longest baseline. All right, so let's get on to how we're going to measure the position. Let's first start with the position. That's maybe a bit easier. So let's start with right ascension. Well, as we said before, the source is drifting east to west over the local horizon of the observer, so the observatory's local meridian, right? As it's drifting overhead, what our radiometer, our interferometer here sees is just going to be a fringe, right? Because the source is offset, right? The interferometer, as I said, is both modulated by the antenna far field response, right, and by the integration period, right? So there's two areas of modulation where this fringe is actually reduced in amplitude by a Syn function and by the far field response, right? So as it's far away from the tracking center, so let's say both our antennas and our interferometer are pointed to the tracking center, right? Then what we're going to see is the source will have some amplitude that is reduced by primarily the antenna response in this case, right? And as we let the source drift overhead, when it's very, very close to our local meridian, it will appear at the top of that fringe function, so it will have a maximum. If it's right at the center of our local meridian, then remember, we'll just be measuring a constant function at some maximum, right? If it's slightly offset, we see a fringe, right? As it moves off this local meridian again, the sensitivity to it is reduced again. Oops, sorry. So if we get the time position on our local sidereal clock that the observatory keeps at that point where the response of our interferometer is maximum, then we can work out the right ascension of the source, of course, right? Because at that point, the hour angle is precisely zero. So the right ascension is going to be given by the local sidereal clock minus this 0 hour angle. So it's just given by the clock. And that is our right ascension. So that's how we determine the right ascension of a source, roughly speaking, of course. Now, let's get on to declination. Now, this is slightly trickier, but still doable, at least for a rough approximation. As I said, we only have one unique spacing here. To localize the source properly, we need many projections, right? So a source at the celestial pole, so either NCP or SCP, either way, appears to stand still, right? So Polaris, if you think of an optical picture of a star drifts over time, it will rotate in the northern hemisphere. It will be rotating around, the Polaris star, right? So Polaris stays roughly still. Now Polaris is roughly at the north celestial pole, right? So at that point, we have a very, very small fringe rate, right? So there is essentially no fringes. It's just a constant function that we measure. Now, if we measure the fringe spacing of a source placed anywhere else on the sky to be about 1.14 degrees, so this is a measurement we physically take by examining the fringe pattern from our interferometer, then at the equator, the fringe rate is going to be roughly this spacing, so there's 1/14 degrees, over about the sidereal rate, which is about 15 degrees per hour, roughly speaking. And that gives us a rough estimation of the fringe rate at the equator, which is about 4 minutes, 53 seconds. Now, in combination with the fringe spacing, we also measure the fringe rate that is output by our interferometer. Now, that fringe rate we measure to be 12 minutes, right? Now, if we compare that measured fringe rate to the fringe rate that we calculated at the equator, then we take the cosine of that gives us the roughly the declination, right? That's just a rough approximation, and in this case, it's going to be roughly 67.7 degrees. Right? So the position with a two-element interferometer if we have a single bright source that we're keeping track of. Now, in order to get an estimation for the size, we're going to be relying on the resolvedness of the source. Remember, I said the source is said to be resolved if the integral of the fringes over the source, so let's say the source is a disk, as we had with Betelgeuse. The disk here is just an arbitrary radius of 0.2. Now, if we integrate the fringes over the source, then as the baselines are moved further apart and the fringes become more and more compact, then the absolute of the integral will tend towards 0, right? At some point, so let's say at some threshold, we say the integral over the source is essentially 0, and at that point the source is said to be resolved out. We get no power from our interferometer if we measure if we move the two antennas further apart. So this is exactly what are the disk diameter of Betelgeuse was measured, right? Back in 1920, just in the in the optical. So at that 121-foot separation of the mirrors, the fringes essentially disappeared. So the integral over the source went to 0, right? And at that point, that gives us the size of the source. So if we look at the grating of our interferometer, so V of U and V, we can also call it a visibility, and now it becomes apparent. Use the phrase visibility function. The visibility function is essentially exactly what it says. It's how visible is the source at a certain baseline distance, right? And because we have a disk here in the image space, right? So in the sky space, we have a disk. We're going to have a airy disk in the grating or the visibility space, right? So in the UV space. So this is just a Bessel function of the first order of the first kind, right? Such a Bessel function as a null, first null at 3.8317, right? And if we plug in our dot product, so if we just constrain ourselves to one dimension for now, just to make this simple, if we plug in our dot product over here, right, that must be equal to the position at which this first null occurs, so equal to 3.8317. We do some substitution, a measurement where exactly on the UV distance this lies, so which spatial frequency is this first null. We get a measurement of about 3.05. We plug that in here, right, and that gives us on the sky for a narrow field approximation, L to be approximately 0.2, and this corresponds very well to the disk diameter that we just assumed in this toy example, right? So let's move on to a real example, right? In this case, we don't know the diameter of the source. We have the moon. We are observing in L band here with Meerkat at about 23 centimeters. Now, again, I plot the visibility. The visibility is now calibrated in terms of Janskis, right? So the amplitudes here plot on the y-axis. On the u-axis, we plot the spatial frequency, so the UV distance, so length of the baseline, right? And now, again, the moon is very roughly a pillbox, so very, very flat disk. It has some structure, but it's really, really flat. So let's assume it's a flat disk and it doesn't taper off towards the edge. So just to make the mathematics here a bit simpler. And we measure the first null here at 30 meters, right? So this is on the shortest, one of the shortest spacings within the Meerkat array. And then as we had before, we're going to set this equal to where this airy function, so the Bessel function goes as its first null. So we can work out exactly the diameter from this measurement that we've taken. It's about 32.15 arc minutes. Now, that is, again, we have the antenna response, so the far field response of the antenna, convolved with the, so the grating that we get from that is convolved with the basal function that we get from the moon, right? So it's going to be slightly extending that. So this is not a bad approximation, given that we can read up online that the lunar disk is about 31 arc minutes in diameter, right? So again, we call this grating function of the interferometer, this UV function, the visibility, exactly because it is measuring the amplitude as a function of UV distance. So this is why it's called the visibility function. All right, and that brings us to the end of our lecture here. I'm going to just summarize some takeaway points, the most important points that you need to know. Well, an interferometer measures the spatial frequencies of the sky brightness distribution. This is called the visibility function of such a distribution. The sampled visibility function acts as a filter to the brightness distribution. So short spacings, those close to the UV origin, measure the very, very large scales in the sky. The long spacings further out on this UV space measures the compact scales on the sky. It is equivalent in sensitivity and resolution to an aperture with an unfilled grating, right? So we can have either a single very large dish, right, which with holes in it. That is going to be exactly the same as having an interferometer between spacings physically separated, right? So, so we've made this relationship. This is provided that the signals from the orthogonal wavefront can be added coherently, right? This is the golden rule. We have to be able to add signals coherently. We can use Earth rotation to fill such a synthesized aperture over time. Remember that the UVW coordinates are a function of our angle, right? And we'll be relying on this when we move on to imaging, and I will show you the effects of not having measurements throughout the UV plane. So if you have a UV plane with holes in it, that has some effect on our image, and we will discuss that in the imaging lecture. Okay, thank you so much for your time, and I'll be taking further questions now.
Thank you very much, Ben. So we only have one question. It's more clarification. Perhaps if you can elaborate just a little bit more on the relation between fringe spacing and angular resolution.
The fringe spacing here is, let's say we've measured the fringe spacing in radians between two peaks along the fringe here, right? So this fringe spacing is under a small angle approximation, right? So where the source is not too far away from the stopping center, is exactly giving us the resolution, right? So it's a very good approximation for our resolution, where our resolution is measured by this Rayleigh relationship, which we'll also call this, by the observing wavelength over the length, the baseline in this case.
Okay, there's a follow-up question here. Could you please elaborate more on the unfilled current grating?
Let's go back to the illumination response here, right? You have a grating function, so current along the surface of the aperture. So if you have a parabolic dish, then it's the current distribution along that parabolic surface, right? That is called the function G U of V. Remember that UV coordinates lie in the plane of that aperture, where if we say the aperture has very little depth to it, it's roughly a plane, right? So it's UV is in the plane of that aperture. The grating is the current distribution along that aperture, and that is related to the far field response of that aperture on the in cosines of the sky sphere. Now, this GU of V is the current, as I said, and that current can have holes in it, right? It doesn't need to be a uniform box, right? As we had for this third example over on the left-hand side here. It can have holes, right? Or it can be non-uniform, right? And all of that all of that gives us a frequency or a Fourier response that has side lobe levels depending on what the function looks like, right? So in this case, we have a grading function which have a bit of reflector. So let's say you have a wire strand here, right, indicated by this box. There is no reflective aperture between that and the next strand, and that, for instance, so if I go back, is the non-cross is a very great example of that. So you have thin strands of wire spanning the aperture here. You can't see them quite in this picture. So they're almost like the size of like a bit thicker chicken wire. So so those strands span these arms here, and that is a great example of non-uniform grading, right? So you only have a reflector at certain points in this UV space in the antenna.